Hello everyone, I'm Chen, a PhD candidate in Harbin Institute of Technology. I'm introducing our research on behalf of all my co-authors. Our research topic is on codeword-based disparity in polar codes. Here are the contents of my presentation. My presentation will include 5 parts: background and motivation of this research, fundamentals of polar codes, codeword-based disparity in polar codes, simulation results, and conclusion. First, let's talk about the advantage of polar code. Polar codes are the first class of error correction codes, which can be proved to achieve the channel capacity of binary input discrete memoryless channels. They have low encoding and decoding complexities and recursive structure. Polar codes can achieve satisfying error correction performance over a wide range of code lengths. Due to these characteristics, polar codes have been adopted as the coding schemes for the 5G communication system. The motivation of this research is as follows. We all know that polar codes are constructed based on the reliability difference of the bit channels. The generated matrix of polar codes is invertible. The input bits can also be represented as the codeword bits multiplied by the generated matrix. Based on these observations, we make an assumption that there are significant disparities existing in the codeword bits of polar codes, and the significance level of codeword bits are relevant to their bit index. Next, let's talk about fundamentals of polar codes. Polar codes are constructed based on the channel polarization phenomenon. Channel polarization includes 2 operations: channel combining and channel splitting. Equation 1 shows the channel combining operation. X1 equals U1 plus U2. X2 equals U2. After combinations, a synthesized channel is created. The capacity of the synthesized channel is the sum of the 2 original channels. As equation 2, the mutual information of the synthesized channel can be split into 2 parts, according to the Qing's rule of mutual information, thus creating 2 virtual channels, W- and W+. The input of W- is U1, and the output is Y1 and Y2. The capacity of W- is the first atom on the right side of equation 3. The input of W+ is U2, and the output is Y1, Y2, and U1. The capacity of W+ is the second atom on the right side of equation 3. The mutual information of the splitting channels and the original channels follows equation 4 to equation 7. After recursive operations of channel combining and channel splitting, a series of virtual channels are created. These channels are called bit channels. This figure shows the capacity of the bit channels when n equals 1024. The original channel is a binary eraser channel with an eraser rate of 0.5. We can see that the capacity of most bit channels is near 0 or 1, as n tends to infinity. The capacity of the bit channels tends to 0 or 1. In other words, this set of bit channels will be polarized into noiseless and noisy channels. This phenomenon is called channel polarization. The idea behind polar coding is to transmit the information bits through the noiseless bit channels and assign fixed bits over the noisy bit channels. The encoding process of polar codes can be written as equation H, where G is the generator matrix, Bn is the bit reversal permutation matrix, and O plus n means the nth Kronecker power. F is the kernel matrix, which is shown as equation 9. Here is an example of polar coding. U1, U2, U3, and U5 are fixed bits and are assigned with zeros. U4, U6, U7, and U8 are transmitting information bits. The structure of this picture is equal to the structure of F's nth Kronecker power. Next, we introduce successive cancellation decoding of polar codes. The log likelihood ratio, LLR, is defined as equation 10, and the LLR can be calculated recursively as equation 11 and 12. The S decision element can be represented as equation 13. Here is an example of SC decoding. The nodes are labeled according to their order when they are activated. First, we activate node 1. If we want to know the LLR value of node 1, we need to know the value of node 2 and node. If we want to know the value of node 2, we need to know the value of node 3 and 4. When the value of node 3 and 4 can be obtained from the channel, thus we can calculate the LLR of node 2. If we want to know the value of node 1, the value of node 5 is also needed. And to calculate the value of node 5, the value of node 6 and node 7 can be obtained from the channel. When both node 2 and node 5 are known, we can calculate the LLR value of node 1 and make a decision about the value of U1. Next, we can calculate the LLR value of node 8 according to the LLR value of node 2 and node 5, also the value of U1. After that, we can calculate the rest nodes similarly. Next, we introduce the construction of polar codes. The LR values given by equation 11 and 12 can be considered as Gaussian random variables. Calculate the expected value of both sides of equation 11 and 12. We have equation 16 and 17. And the error probabilities of the bit channels are given by equation 19. The next part, Codeword-based disparity in polar codes. First, let's talk about the BLER performance of polar codes over non-uniform channels. For the basic unit of encoding and decoding shown in this figure, we have equation 20 and 21. And the block average of polar codes is calculated as 22. To research the significance disparity of codeword bits with different positions, we transmit the codeword bits through non-uniform channels. Some of the codeword bits are transmitted through the pure noisy channels, which can be seen as punctured bits, and the other codeword bits will be transmitted over the AWGN channels. Consider a codeword bit X subscript I, which is over the pure noisy channel. The LLR of X subscript I can be calculated as equation 23. To show the various significance disparity of codeword bits in polar codes, we use punctured bits to equalize the codeword bits transmitted over the pure noisy channels. We consider the polar codes with code length 256 and the code dimension is 93. This figure shows the block average performance of polar codes by randomly punching 30 codeword bits in different sites. The sites are shown in these slices. It can be found that the block average performance of scheme 3 are better than the other schemes, which implies that the average significance levels of codeword bits in the third site are lower than the code bits in the other sites. We also provide the block average performance of polar codes by randomly punching 20 codeword bits in the aforementioned sites. We can see that scheme 3 also has the best BLER performance. It's shown that there are various significance levels between the codeword bits, and the significance levels of the codeword bits will be affected by their positions. Thus, we make an assumption that the codeword bits in the middle sites are with lower average significance levels than the others. We define 3 puncturing schemes. The puncturing sites are shown in the slices. The block average performance of these 3 schemes are given in this figure. When 60 and 30 puncture codeword bits, it can be seen that scheme 2 has better performance than the other schemes, with both numbers of punctured codeword bits. Note that the puncture site of scheme 2 is still in the middle site. Then we focus on the schemes with better performance than the others in previous results. For simplicity, the puncture sites are shown in these slices. We term this as scheme 1 and scheme 2. We can see that scheme 1 has better BLER performance than scheme 2. From this, we can conclude that continuous impulse noise will lead to much more negative effects on the block average performance of polar codes than that of discrete impulse noise. In this figure, the BLER performance of puncturing code word bits from different sites with different probabilities are shown. It can be found that scheme 4 can be equalized as randomly puncturing, and scheme 3 has better performance than scheme 4, which means that randomly punching cannot be optimal. This figure also shows that the middle positions are with lower average significance levels. Next, we compare the proposed schemes with other existing puncturing schemes. We can see that our proposed schemes have similar BLER performance as the IMP, and the performance of QUP and RQUP are not very satisfying. This means these two puncturing schemes cannot fix the position when the polar codes are with fixed information sites. Here is the conclusion of this research. In this paper, to receive the significance disparity between the code word bits of polar codes, we adopted non-uniform channels to transmit the code word bits. By analyzing the log likelihood ratio of a code word bit affected by the pure noise channel, we equalize this bit as a puncture bit. By studying the previous research, we made an assumption that the significance disparity of code word bits would follow a symmetrically distributed law based on their positions. The simulation results prove that the significance disparities of code word in the polar code exist. Thank you for listening.